Yeah. So by the way, how do you like the paper?
Um, it has a lot of like a mathematical formula, but when I spend a lot of time on it, I think it's not really hard to understand now.
The physical meaning of the formula is straightforward, right? I mean, try to approximate to the rank 1 matrix, right? To see the difference, right? And then they derive some bound there, and also very similar, right? So the physical meaning is very easy to explain. Probably the derivation process is somewhat complicated, right?
Right, because when I first time see this paper, I see a lot of formula there. I'm a little scared of that, but after I see about attention is all you need, that paper, and compare that paper to this one, and many things make sense. To be honest, yeah.
You don't be scared by the math. I mean, math is also just one language. Try to express some idea, some information. It's the same as a tag, as a natural language. I mean, this words, right? It's another system language actually. So all the thing is to express idea and the information.
Yeah, but I do think this kind of papers can really make some change of the like attentions or transformers, because before you maybe change some parts of them, you need to know why they have this kind of like attention, like residuals there. So I do think this kind of papers will do help to me.
Yeah, try to explain something, right? Because we propose something there, then we need to explain why it works, right? So this is like a follow-up paper to explain why it works, right?
Right.
Yeah, I think the time probably is up. And so, hello everyone. So today we will discuss a paper. The title is called "Attention is Not All You Need." Right?
Yeah.
And so this is a follow-up paper of the transformer paper. Right? I assume you have read the paper on transformer already. The title of transformer actually is called "Attention is All You Need." Right?
Yeah.
This paper tells a different story. And the presenter today will be Doubly Exponentially, and so Doubly will share her idea with us, and I will give a time to Doubly. Yeah, you can start when you are ready.
Okay, hello everyone. I'm Doubly Chen, and today I want to introduce the paper to you. It's called "Attention is Not All You Need. Pure attention loses rank doubly exponentially with depth." And in today's lecture, we will have like a problem description at first time, and then we will have some background definitions, and I will share the main idea of the papers with you. And then we will go in details like the methods and techniques talked about in these papers. And the papers also give us 3 experiments to show the phenomena they said, and also give us the result of the paper. And then also have some related works and potential future works. Okay, let's begin. So the first things I want to talk to you is problem description. And through the papers that we've been working on in this course, it is not difficult to see that transformers has not only been used for the basic task of like a natural language processing, but also had a huge impact in the fields of computer vision here, like or speech signal processing or multimodal text and so on. And attention is that all you need? We have this kind of problem. And the paper we talk about today seems to be closely related to the father of the transformer. Just the professor mentioned earlier, is attention is all you need. And the reason I chose it at first time that the name of this paper just seemed like to want to fight with transformers. So however, I believe that after reading it, you will find that this article is actually a profound analysis of what makes transformers great. So the whole article is looking at just one question, that is, why is transformers effective? When we fully understand why attention-based architecture are effective and explore existing models roughly, and we can design more effective models, I think. So I will give you some background definitions because as this paper is based on transformers and includes a lot of mathematical proofs, I'm going to start by taking you through some basic concepts and transformers in an accessible way. Okay. And first of all, we will talk about the mathematical concept called Lipschitz continuity. And it actually describes the upper bound of the slope of the points on the function, which means that Lipschitz continuity function is the limit in how fast the point on the function can change. And there will exist a real number for every pairs of the points on the graph of the function. The absolute value of the slope of the line connected them, it is no greater than the real number. And the smallest such bound is called Lipschitz constant of the function. And you can just imagine that it's a smoother condition than continuous. And the next mathematical concept, we call it norm. I think everyone knows norm, but this norm is not for vectors, but here we are using the norm for matrix. And here we have L1 norm. This is the sum of absolute values of elements in each column of the matrix, and then take the largest of them. And next is the infinite norm, the sum of the absolute value of each row of the matrix, and then take the largest of them. And these two is just like the same because the only difference is here is column and this one is row. And so in this paper, we have defined something that combine these two norms, and that seems to combine the maximum features of the row and column. So I don't think it's really hard to understand. And we also have next concept called inductive bias. And I will give you a simple example of that. Like if I have an apple, and if I imagine Apple, maybe I would think about its Apple company, like iPhone, like iPad. And if I give the apple to an artist, like a Picasso, it's Picasso's really famous painting called Guernica. And Picasso is who excellent in use of rich forms, namely space, color, and line. After the age of 30, Picasso entered a period of restless exploration, and his work were as restless as his life. So without the slightly unity and continuity and stability, you can see the picture here. I think it's really weird because you can see many like angle here, like a triangle, like a really weird. And so if an apple is in Picasso's eyes, what will it look like? Maybe it look like this one. And you can see also have many angles, no continuity and stability. So maybe it's weird, but it's maybe in the Picasso's eyes. And I also want to give you this drawing. It's really famous called Starry Night. Starry Night is from Van Gogh, was a colorist painter. He's a colorist painter, and his preference for color is almost reach a state of madness. So you can see he used a lot of color here, and the colors in his painting are bold and exaggerated. And because I'm not really have a deep understanding of art, I see this kind of picture is full of textures, full of colors, but it's really beautiful, right? And if the apples is in Van Gogh's opinion, maybe it look like this, like also have many textures, have many colors. Or Monk, I think he is also a real famous painter. And he takes his life, death, love, terror, and loneliness as senses and express his feeling and emotions with strong contrast line and colors, blocks, and concepts and exaggerated shapes, like the screen here, this picture, this drawing is really weird with some shapes here and some color blocks here. So the apples in his eyes maybe just like this one. It's also in a really weird shape and some color block, like here is red and here here is yellow. So maybe it's apple in monk's eyes. So as we can see from these apples, different people maybe have different characteristics. So the same event or object is often interpreted in different ways. So I do think like inductive bias is a similar concept, but it's talk about not human beings, but machine learning model. So each model has its own reasoning preference because of its different objective and evaluation method. And this property has nothing to do with the data set. Like, for example, in the linear regression, the model assumes that output or dependent variable is related to independent variable linearly. So we have like a table here. Maybe we have this kind of deep learning components. We have like fully connected. We have convolutional, recurrent graph network, and they have different entities like units, fully connected. The entities units, and to the convolution is grid elements, just like the filter. Yeah. And the recurrence is time steps, and to the graph networks, it's nodes. And the relation to the fully connected is OR to OR because it's fully connected. Yeah. And convolutional is local because it can just can see the relationship between a small area. And the recurrent is sequential, and graph network is ages because like we have our nodes, and ages is the relation between the nodes. And so it also can be the inductive bias of every components. Like if we have fully connected, maybe the relation to every point is really weak. But if it's in convolutional network, maybe it will be locally. And the recurrent will be sequentially, and the graph network will be arbitrary because if I have a point, I have a node, I'm not sure the other nodes are maybe anywhere. So it's arbitrary, right? So for example, like convolution, its green elements are filtered, which can consider the relationship between the points in a small area. So it is suitable for doing some analysis about images. So this kind of characteristic will make it more suit for some specific kind of like images, like word, these kind of things. And the next concept called the rank collapse. This is a very terrible phenomenon, to be honest, because the output of each layer of the model is one sentence feature matrix, and each row here, each row of the matrix represents the feature vector of a word. And the rank collapse should mean that each row of the feature matrix tends to be the same. It also means the feature vector of each word tends to be the same. And it means that every word in the sentence will not have any weights. They are almost the same in the computer eyes, right? So it's a really terrible phenomenon. And so the output of the convergent doubly exponential to rank 1, we call this kind of rank 1 matrix rank collapse. And the next step, so this kind of rank 1 matrix, it doesn't make sense to us. So we trying to avoid this kind of things. And the next step is the model review, because this whole paper is just to analyze the transformers. So we will go through the transformers. And transformers contains 2 big parts of it, like an encoder and decoder. And in the encoder, we have multi-head attention, and in the decoder and the feed-forward neural network and residual connections and layer normalization steps. And decoder, we also have 2 multi-head attention, also feed-forward neural network, and 1 more linear mapping decoder layers. So in the right hand is a transformers block. And just like we see in the left, we have these kind of things, and we'll put X into it, and you will have to do something into it. And the main point is that inside the transformer, we have these 4 parts, like multi-head attention, feed-forward, and residual connection, and normalization. And because I'm going to talk a little bit more about the internals of attention, because we are going to use some of them later. So we'll go in details a little. Like in the self-attention, what we have done is we have a sentence. At first, we will have a sentence and we will take into part of characters. Like in this example, we have 6 characters here, and we'll do the word embedding and precision encoding to mix them into the matrix. So in this matrix, every row represents a word. Yeah, and next we will have 3 matrices, weight matrix. The first one called query. We also call a WQ. And the second one we have K, we call it WK and WV here. And what we have done is, because this is a multi-head attention, so we will take into 3 parts. The head number is 3 now, we assume that. And so we will put into Q1, Q2, Q3, K1, K2, K3, and V1, V2, V3. So we will do some calculation, like with the input X, we'll multiple with WQ, and we will have Q. And also the same calculation with K and V, because the WQ was divided into 3. So we got is Q1, Q2, Q3, K1, K2, K3, and V1, V2, V3. So next calculation is we multiple Q and K together, and multi K, K times Q times K. And so we got this kind of matrix, and we'll do some softmax of it. And then we also multi V at last. And because we have Q1, Q2, Q3, so actually we have 3 parts of this matrix, and we'll just combine them together to get a size also the same as the input X. They have the same size. Also, okay, that's all of the attention, self-attention system. So we will use it later. Okay, let's move to another part. And in this paper, we analyzed a SAM. We call it SAMs. It's a pure self-attention network, which means that transformers without skip connections and multi-layers perceptron. And you can see this is the transformer block, but we only want this part. It's multi-head attention, and we call it sense. Okay, that's we move to next part. It's the main ideas of the whole paper. And first, we follow the author's steps. We explore the internal structure of transformer in depth. We first put attention out separately here, and we call it sense, and decide the path decomposition method for analyze. And the second part is we will find a sense process a strong inductive bias towards token uniformity, and it also called rank labs. Yeah, just like the same, like a rank, just the rank 1 matrix. Yeah, we also call it rank labs. We found this kind of phenomenon. And the third part is because you know that transformers works really well, but we also said that rank labs is a really horrible, terrible things. So it's really because the transformer has another part like skip connections, MLP, normalization. So we will see the influence of other parts of transformers on the rank labs. Revealed opposing impacts between the self-attention and counter-reacting force to the rank collapse. And so the whole ideas can summarize by these 3 points. This is one is path decomposition. The second one is rank collapse. And the third one is the influence of other parts to the rank collapse. So we will learn these 3 parts in details next. Okay, and this part is methods and techniques. So we will first start the path decomposition, and we can see this image here. It's a structure of the sense. We have like L layers here, here 1 to until L, but inside every layers we have many heads here. Like SA1 means head 1, and SA2 means head 2 until we have SAH means we have H head inside one layers. And we also have the skip connections. Of course, if in a sense, we don't have this line, we don't have this skip connection line. But it's in the transformers, right? And you can see that for under SA1, it is calculated by Q1, K1, V1, as I said earlier. And like these right lines, express one pass of the one pass. You can see that in layer 1, it goes through the head 2, and in layer 2, it goes through the escape connections, and until layer L, it goes through the head 1. So we say this is a pass, and we can have a lot of paths in this whole model. And it's from the image, but what about from the mathematical view? Like here, we have this formula before, like we can calculate attention layers, the output of the attention layers. So we can multiply Q to K and also multiply V and do some softmax. And what difference between this one and this one? The only difference is here is a subscript. The subscript is H. It means head. It means that we will divide Q into every head. Like I said before, we can have Q1, we can have Q2, we can have Q3 if the head is 3. Yeah. So you can see this formula, pH equals to softmax, da 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 da. And I also tell you before that X multi WQ means that big Q, E equals big Q, and X multi WK means big K. So the difference between these two formula is only the bias. This don't have bias, but this adds some bias, but nothing really different. So we can see that it's just the same. This pH is just the same as the softmax here. And also we can see SAH, this formula. We can see what is different is like we multi X into WV. This part is just the big V, big VH. So this part is just the same as the whole formula here. So this SAHX formula is just the same as the attention QKV, this formula, right? So the only difference is just here we have H, because we will learn different paths of because this is a head, but it's also a path. So we need to analyze every head. So we need to divide the head into separately. And then maybe we'll put them together. The output of each SAM layer is formed by concatenating the individual output of all H heads and linear project them onto a subspace of approximate size. So we just combine them together into one. Yeah, this is one head and we just combine it. And then the SAM output is given by XL, and the only difference between it's just to put the layers together. And this formula and this formula, the only difference is here. We call it head, but it also can be a pass, but they're all the same, like head or pass. So we'll write in the pathway. The output, so this formula is the output of L layer self-attention network with H head per layers here. Yeah, so it's just the output of one layers. So the next thing is to find this phenomenon is rank collapse. And this might look really complicated, but we can focus on L, I think. The left side of the formula here, the left side of the formulas here is represent the residual of SAM, And the right side represents its upper bound. You can see that. And in the paper, it shows that in the parentheses is smaller than 1 for all the small residual inputs. And you can see that L is on the power to the power, like L is the power of the parentheses and also the power of 3. So which is a double exponential. We call it double exponential, which means that as long as L gets a little bigger, a little bigger, the whole left half, this part will get really large, really small, like very close to 0. If this part is close to 0, sorry. If this part is close to 0, it means that the whole right part is close to 0, right? So it means that the residual also close to 0. Which means that the residual decay will decay really fast and converge within a few times. And it's the single heads condition, but if we are in the multi-head condition, the only difference is the H, because we have multi-head now. But you know that head is 1, 2, 3, this kind of thing, so it won't be really large. So it won't do anything good to the whole formula here. So it also will doubly exponential rate of converge. So it still will converge to a rank 1 matrix. So this kind of thing will appear. We call the phenomena of rank collapse, just that such phenomena is really severe. So what exactly prevent the impact of this kind of phenomenon? It's the next things we are really curious about that. So we'll first think of skip connections. When skip connection is considered, the path decomposition parameter should be modified. When H, so we can see the difference is here. Can you see that? And H is belong to big H, but now it also belong to 0. If the H equals it to 0, it means that skip layers. This kind of things will first, they will increase the number of paths from L to this one. I will explain why they will increase the number of the paths. Like maybe we have a simple example here. We have 4 layers, and every layers will have 3 heads. And if there is no skip connections, maybe we will have 3 powers of 4. This kind of these numbers of paths. But if we add if we can skip 1 layers, we will have this kind of, like L equals to 3 means that I will go through 3 layers, like the blue line here. We can skip the first layer and go through the last 3 layers, or the pink lines, we can go, skip the 3 layers, and we can also go through the 1 to 4 layers. So we have many choice, like we will have 4 layers in the whole model, and we will choose 3 layers of it, and the rest 3 layer will have 3 powers of 3 here. So this also is just one situation and condition, and maybe I can equals to 1 to 0, 1, 2, 3, 4. So you also have many paths, number of paths than the no skip connection one. And also this paper also shows that we can deduce an upper bound on the residual output of the L layers, which means that the residual does not rapidly descend to rank 1. Like here we will have this lower bound. It means that it won't descend to rank 1. Therefore, skip connection can effectively prevent phenomena of rank collapse. And the next one is MLP. We have talked about the Lipschitz constant, and here we use Lipschitz constant called lambda. And the lambda is inside the parentheses, and because the lambda can be big, So this print is inside the print is, it can be a little bigger. So this this right part will not converge to rank one matrix really fast. So the more powerful the MLP are, the slower the converge becomes. So it can slower the whole rank collapse. So it will be helpful for that. And what about normalization? And we can see that their normalization is accomplished by rescaling and shifting the input across the feature dimension, but actually the right multiplication cannot increase the rank of the matrix, so it will play no role when we prevent the phenomenon of rank collapse. And next part is experiment. Next, we will use diagrams to represent the phenomenon we have just described. And the first experiment is visualizing the bias of different architectures. And in this experiment, our data set is 32 samples of 128 token excerpts of biographies from Wikipedia. And the experimental model we use is BERT, Albert, XLNet. And the performance evaluation is the relative residual. Like here is a residual of the SAN X, and here is the SAN X, just the output of the SAN. This is the residual of the SAN of each layers to output before and after the networks have been trained. Okay, let's see the result of the pictures. We can see that from the column, we can see that the relative trend of these lines hasn't changed much. Like here, the SAN lines is collapsed really hard, and other are better, and this also. So we can see that the relative trend of these lines hasn't changed much. It means that rank collapse has nothing to do with the training of the model, but the structure of the model. And you can see in one pictures that pure attention converge rapidly to rank one matrix, like this line here. And if we add some skip, it will work better because it don't just collapse really fast. And but as can be seen from the lines, the result of drawing MLP are still similar to those without drawing MLP. Like the lines SAM is here, but SAM plus MLP also the same way. The paper said this kind of phenomenon because you don't have rich training. It just pulled out the MLP, so it won't be great. But if you retrain the whole model, maybe it will be better than that. However, the figure still shows the significant effect of adding skip connections. Like here, we use different model here, but we got like the same result as soon as the skip connection are removed or the networks exhibit a rapid rank collapse, like here, really, really hard. Here, and the collapse is really obvious. And the second experiment we done is rank collapse in real architecture. And in this experiment, our data set is used to predict two curricular arcs in R2 of radius 0.3 and start at these 2 points, and respectively, each direction counterclockwise and consists of 1,000 points. And the experimental model is a single layer transformers applied to predict a simple 2D curricular sequence, right? And the performance evaluation is a hypothesis that at inference time, the prediction trajectories of the two arcs will converge to the same point. And this, if they converge to the same point, it indicates you will have a rank collapse rather than following the training trajectories. Like we see the pictures here. And in the Y line, we have no MLP, no skip, and MLP no skip, and no MLP skip. And you can see, and in the X line, we will have dimension 32, 86, 128. And you can see that in the first row, it will easily converge, is really fast converge, because they are just in the same time. All the pictures are in the same time, but the first line here is easily to converge. But you can see in the second line here, the first is easily to converge, but the second one and third one is not really easy to converge. So this kind of things means that adding MLP or skip connections either stop or dramatically slow down the rank collapse. You can see that because this one is no MLP, they converge really fast. But in the second row, it don't have skip but have MLP. It's not always converge really fast. And if it has a skip connections, it will not converge really fast. And the third experiment is path effectiveness. And in that, we have 3 different tasks. First is sequence memorization, and the second one is learning to sort, and the third one is convey or predictions. And we have different data size. Like here we have 500 English sentence from Wikipedia and New South. And here we have the training and test sets consists 1,200 sequence respectively. And in this task, we have training set consists of 10,000 sequence of points. And we use the same experimental model. Like here, we'll use, and all of them we use entire model. We also use random predictor, and we use 5-pass model and 20-pass model. And we have different performance evaluations here. Like in the first task, we will solve this task. A model needs to memorize a predetermined mapping from natural language sentence and random label sequence of the same length, and test the train to minimize the cross-entropy loss between the predicted and the ground truth label. And we also have the learning to sort this task, and it will give an input sequence of letters. And this task learn to sort letters in alphabet ordering, and the model's output for each input letter is used to determine the position of that letter in the predict ordering. And we also have the third task is given a sequence of n points uniformly distributed in this size and shifting by a random bivariate standard normal. And this task predicts the converse whole of these points. And so we can see the images here. The X line, the X is path length, and it's from 0 to 6. And the Y is token accuracy. Also, it's a little different between these 3 pictures here. And we can see in the memorization task, of course, the random predictor is 50% right. And if it's entire model, it's higher than 60, almost 85% right accuracy. And we can see that a 20-pass model is better than 5-pass model. And this kind of the same results is also can apply to these 2 tasks. We focus on, like, we have the path length. If the path length is equal to 1, you can see that in the first task, we will the 20-pass accuracy will higher than 80%. And in the second task, in the path length equals to 1, the 20-pass accuracy is higher than the 60%. And in the last task, we can see that if the path equals to 1, the accuracy of the task will higher than 60%. And if the path being longer, like the path length is equals to 5, you can see that in the first text, the accuracy will be lower than 50%. And the second test also lower than 50%, lower than 10%. And in the third test, it's a little bit higher, but to the whole pictures, it's not really high. It's nearly 60%. So this picture shows that the rapid diminished effectiveness of paths with respect to length indicates that the transformer relies almost exclusive on short paths. You can see that when the path going longer, it won't be the higher accuracy. So the last part is it's not the last part, but the part is results. As we have talked before, that we first is path decomposition, and in the paper we create a new method. This paper presents this path decomposition method, which can easily prove the phenomenon that rank will converge quickly and clearly see the problems of rank collapse. And the second one, I call it observed phenomenon. This phenomenon is rank collapse. Like in the paper, self-attention process a strong inductive bias towards token uniformity without skip connections or MLPs. The output converge doubly exponential to a rank 1 matrix. And the rank 1 matrix is also, we call it token uniformity. It's the same things. And the third part is the influence of the other parts, and also correlate analysis of the reasons. And it shows that skip connections and MLPs stop the output from degeneration. And the skip connection play a key role in mitigating rank collapse, and MLPs can slow down the convergence by increasing their Lipschitz constant. And you know that we have taught that like a skip connection can play an important role because he gives the residual lower bound, so it won't be rank collapse anymore. And so the paper also mentions some related works, like skip connections were first introduced by ResNet, that we all know that. And ever since, it had been used to facilitate optimization in deep networks. And the skip connection in this paper prevent the transformer output from degenerating to rank 1 and exponentially quickly with respect to network depth. And also some research found that the length of the effective paths in deep precision net are much shorter than the total network depth. And in this paper, we always also find that sense relies on short paths to avoid rank collapse. By these pictures here, we don't need to have a long path. We can have a good results. And also some recent works have approximated attention matrix with low rank factorization or kernel method to reduce the quadratic self-attention complexity. And also have some researchers have been recently advanced in understanding the theory behind transformers, like prove the theory universally and provide necessary and sufficient condition for attention to simulate the convolution. And Lipschitz constant of self-attention was analyzed. And what about the potential future work? First one is how can we take full advantage of the revealed token constant inductive bias to design more efficient networks and perhaps better utilize long paths. As you can see from the graphs above here, the path length above 3 doesn't work very well, but we know that deep neural networks tend to extract finer features. So it's important to see if we can make better use of long paths. We can maybe find a way to avoid this kind of collapse and use a long path model. And the second future work is, what does the width and depth trade-off actually means? And this question is also an indispensable question to discuss the deep learning model. Like I think in the attention system, maybe the width means the head numbers, and the depth means the layers of the whole architectures. But because now we find that if we have more layers, we have the problem of rank lapsing. And if we can have a way to avoid this kind of things, maybe it can be longer than now. And the third future work is how to prove a meaningful lower bound or residual convergence for transformers. And we know that skip connection is effective because it gives a lower bound to the residual drop, and it will definitely prevent the rapid drop of the rank. So if we can find new things, maybe it's not skip connection, we can give the residual lower bound, maybe it can replace the residual, and we can avoid this kind of rank lapse. And that's all my presentation, my lectures, and this is the reference here. And do you have any questions? About?
Yes, the talk is very good, and then you illustrate the main idea of this paper already. Yeah, any question from the audience?
Do you have any questions?
Yeah, first of all, thank you so much for choosing this math heavy paper. I think this was like one of the hardest papers so far, especially to explain and understand the math behind it. My question was, my question was about the interpretation that like longer paths are not like so expressive. But like when I think about like all those architectures, I think that like even though these longer paths, like if we just like pick those longer paths and make a prediction using those paths, even though the accuracy would be low, I think like they in general already just like contribute to the general accuracy of the model. Maybe they have like another task, maybe they're just like fine-tuning the results or whatever. But like if they wouldn't be necessary, then like we would already be using like much shorter, like much shallower transformers. Like I don't understand if like those longer paths having like by themselves a low accuracy would mean that they're not like expressive or they're not like useful for the network.
To be honest, I don't think we use like a shallow model now, because like a transformer, maybe we have many blocks of the attention. So like what we use now is also long path things, because I think like the skip connection can avoid this kind of things. So we don't worry about like long paths will have a rank lapse. So actually, because this analyze just tell us that maybe shorter paths will be useful than the long paths, but actually what we use is still the long path, I think, because the skip connections can avoid this kind of things. So maybe if I want to do something, maybe I want to find another way to avoid rank lapse.
Yeah, I see. Like what I understand from the help of skip connections is that they introduce shorter paths, which indeed just like they introduce shorter paths, and then shorter paths bring the accuracy. That's like what I understood from their like conclusion. However, like it's not only the shortest paths that just like contribute to the accuracy, because if we only have chosen the shortest path, then we cannot reach the like optimal accuracy. But yeah, I agree with you that like there's probably something that also the longer paths bring.
Yeah, I do think so. Yeah. You said that this task maybe if if it's in a shorter path, it shows that the token accuracy is still really high. But I think maybe it's just in this kind of task, but if I change it into another one, I don't think it will work so well like that, because in only like 1 or 2 layers are a model, I don't think it can work really well. So I don't think, I think the most problem is to try to avoid rank lapse, but not to shorten the path length. Can you hear?
Yeah, I understand. Thank you.
Thank you. And does anyone have any questions?
Yeah, any more questions from the students?
Any more questions?
This is not an easy paper, right? You should have questions.
Do you have any questions?
Okay, so if a student have no question, then probably, the talk is very good, right? It illustrates the main idea of the paper.
Yeah.
Also, for me, I think, so some of the ideas in this paper are interesting. However, the analyze part is very different from transformers, right?
Yeah,
it focuses more on the attention layer or the attention component. And in the real world, the transformer, maybe can you go to the transformer, is architecture. In the transformer, we have this feed-forward layer, right? Or the multi-layer perception layer, which is stacked on top of the attention layer, right? However, in this paper analyze, they remove this kinds of feed-forward layer and it just focus on stacking multiple attention layer on top of each other to analyze its performance, right? So then they can draw the conclusion that, there will be some like a collapse of the rank of the matrix, right? After feeding the input into this kind of attention layers. If we have a deep architecture, then the result will collapse to a low rank, like a rank 1 matrix at the concluding this paper. So in the real world, if we use transformers, because we have stacking this kind of feed-forward layer on top of this attention layer, this is more like a block, right? And we have multiple, we have multiple blocks on top of each other. It's not just stacking multiple attention layers, right? So it will be very different from the analyzed result in this paper if we use transformer in the real world. So, but the idea is very interesting. This paper also reminds me about another paper. It's on the almost smoothing of graph neural nets, right? The analysis is very similar, and they also draw a very similar conclusion compared with over smoothing of the graph neural nets. This paper also, the over smoothing paper also focuses on analyzing, it's more like a Markov chain or some propagation among graphs, right? So they draw the conclusion, if we have some like deeper graph neural nets, then the result will be we converge to the same representation for all the nodes. I think they have a similar conclusion in this paper, right?
Yeah.
So the ideas they are shared among different domains actually. The idea is very interesting, but the analyzed results, they're based on some assumption. They just have this attention layer. They don't have this kind of feed-forward stacking between them, right? Then they draw the conclusion in this paper. I think that the talk is very good, and it can provide help us understand this paper much better than just reading the work, right? Yeah. So, any more questions from the students?
Yeah, can I ask a question real quick?
Yeah, sure.
So for the interpretation of figure 2.
Figure 2?
Yeah. On the top, they have the...
Which one? Sorry.
It's the one with like the randomly initialized transformer models and then the pre-trained transformer models, the BERT and Albert and XLNet. Like the empirical results.
This one?
Yeah, exactly this one. So the dark blue line, not the purple one, that's the transformer, but the other one, the dark blue one. It seems like there's kind of a difference in the patterns starting from a randomly initialized model and starting from a pre-trained model. So from the randomly initialized model, the SAN plus skip, which is, I guess, the transformer without the MLP, right?
Yeah, right.
Does like kind of equal performance or better than the full transformer architecture, right? When we're talking about randomly initialized, like the top row.
To be honest, because this I have said that like in this paper, they just cut the MLP. So actually this picture is not really accuracy because they don't have a retrain. They don't retrain the whole model.
Oh yeah, so
you can't see the lines here really carefully, I think, because if you retrain the model, maybe you will change a little.
Yeah, so the metric is the relative residual, right? Not not accuracy.
Yeah,
but still, like higher relative residual as you go further into the model is desirable because it's indicating the rank is not collapsing, right?
Yeah, we can just see this this collapsing one between this is not collapsing, but it's really hard to say if we don't have MLP. You said it will be lower than the have MLP ones, but I think it's because of the retrain things.
I'm mostly interested in the difference between the SAN plus skip without MLP. The difference between randomly initialized and pre-trained. So like compare the dark blue lines, top versus bottom, and it looks like the patterns are very different.
Yeah, right.
Like noticeably different. So I'm curious if you have an interpretation of that. It seems like the authors kind of just hand waved it a little bit and said, you know, oh, it's pre-trained, the MLPs are changing the token distribution, you know, don't worry about it. But I don't know if you have a more like nuanced take than that, because I was curious. Especially ExcelNet looks very weird. Pre-trained Albert, it looks like taking out the MLPs leads to almost the same performance as just taking out everything, right? So yeah,
maybe if I have time, maybe I will do the same experiment, because maybe retrain is not really hard. And if we can retrain it, maybe we'll have a more accuracy answer for that.
Yeah, maybe also like here, like when we look at the residual, like it's a very hard metric to interpret. Like I imagine like if the residual is very close to 0, it's definitely a sign of like, it's definitely a bad sign. But if it's like high, it doesn't show us that the model is like better than the other, because like, I mean, it can have a high residual, so we know that it's not rank 1, but like it having a higher rank doesn't necessarily mean that it makes a better job. So I mean, so like only thing here, like only conclusion that I can take from these are that like some of these lines converge to 0, so some of these go to rank 1, which is definitely bad. But for the others, like they don't converge to rank 1, and then we cannot say anything about them. Actually, this is what I understand.
Yeah, we only can see the SAM and the other model, but we can't really carefully compare the other 3 lines here. I think it's a not really accuracy experiment.
Yeah, this is why here is the artificially created metric, right? I mean, it defines the decaying rate, also based on the residual term they define in this paper. I mean, define the approximation or closeness to a rank 1 matrix, right? So the close, if the y is close to 0, it means a very bad sign. However, it doesn't necessarily mean, I mean, if it is high, it's better, right? So yeah. Yeah, any more questions or ideas from the students?
Any more questions?
Okay, so I mean, so as you can see, we have so many papers on transformer. I mean, I'm not sure for the students in the class, if you haven't read the transformer paper, I'd like to recommend you read the paper as soon as possible. We will have some more to come in the following, schedule spreadsheet. We will have so many papers on transformers in this course. The main reason is because in recent years, the transformer has generally dominated many research areas already, right? In computer vision, in natural language processing, in graph learning, the transformers, they are probably the hottest model used nowadays. So if you still don't know transformer, please read transformer paper as soon as possible, right? Yeah. Also, another reminder is for the final paper, I mean, you may need to, start to work on the proposal for your project or for the final paper. You can discuss with your teammates. If you work on, you also need to decide by yourself or for the problem you plan to work on. Also design a detailed plan for the project. Then also you can start owning it. Right? If you have time, then you can start to work on the project or work on your paper. I mean, maybe from today, right? And you can start owning it, then you don't need to rush at the very end. Okay, so this other reminder I have for you, and the talk is very good, and thanks so much, Jiabei, right? So the talk is very good. It illustrates all the necessary ideas of all the information for the paper already. Yeah, thanks so much.
Okay, thank you.
Okay, so if you have no questions, probably that's it for today, and thanks so much for your time. Yeah.
Thank you.
The Jiabei, probably you can leave for a few minutes, then we can talk, right?
Okay.
Yeah. Yutong, do you have any questions? If you have no question, then probably I can kick you out from the meeting. Let me remove you. Yeah, so 这个报告很好了，基本上你应该能 get 到这个文章的大意。
对，我觉得因为我看了挺久的，然后就刚好也把 Transformer 那篇文章又仔细的过了一遍，我觉得。然后这个方向本来文章就大部分是创新嘛，然后它这篇文章又刚好是就是分析 Transformer 的东西，所以我觉得这个方向也有点有意思，反正。
就看你的兴趣了，就是一般我们喜欢就是提一个新模型嘛，但新模型提出来如果能 work 的话，就会吸引一堆人来用。用完之后，人家就会好奇为什么可以 work， 是吧？他们就会分析一些东西。就这篇文章有点像有点像个打扫战场的一个文章。
对，我就觉得它跟我平时读的就很不一样，它就是更像，它感觉就是虽然它现在有个东西出来，但是那篇文章也的确没有很好的说明说啊，它每一个部分有怎么样的用处。就是它给我的感觉就是那种可能我把一篇文章拿出来，它的每一部分去分析它，所以我觉得这种也很好。就是说我怎么样去添加一些东西。
就是有些人他的兴趣可能就是提新东西出来，并且保证这个新东西是可以 work，他并不在乎做一些什么理论分析，他可以通过实验来证明他模型是可以 work， 是吧？有些人他是喜欢通过一些理论分析来证明为什么可以 work， 那 derive 这 bound， 是吧？这可能跟人的背景、跟人的喜好都有关系，就看你喜欢了。然后你也可以思考一下，你到底是想要做什么类型的科研，未来的话，是吧？就是你应该也读了好多文章了，你可以
对，我最近也是托这个课的福，也是真的是看了很多，而且我发现就是 Transformer 真的是可以用到各种地方，就是感觉对呀。
最近学术界基本上都是在做 Transformer，
对，好像大家每一篇文章讲的里面都是包含了。就老师，你有没有就是对于 Transformer 就是像这种类型的文章，就比如说去分析它内部的文章，你还有没有更多的别的文章推荐呢
？Transformer 最近我倒是看的比较少，他们更多都是偏应用，因为 Transformer
还是偏应用
模型啊，他们
对，因为它效果很好了。现在大家因为它效果好，所以也应该不太会说再去看它里面的东西。
他们有些是对 Transformer 是做提速，他们之前有些人做什么 Performer 的，我等一下我搜一下。
好。
就是大家都是在改进 Transformer 啊，他们也会提出一些新的想法，然后我可以发一个给你，我先把这个 recording 停掉。
哦，好。